Hi, I'm Cole.
And I'm Grace. Welcome to the Deep Dive.
Welcome, deep divers. Today, we're embarking on a really fascinating journey into the mind of a true visionary. Someone whose name, might not be splashed across every single AI headline, but whose work, well, it laid the absolute foundation for the AI revolution we're seeing right now.
Absolutely.
We're talking about Dr. Terry Sejnowski, a really central figure in our series on AI Visionaries, the founders. And our mission today, it's basically to unpack how Sejnowski, who actually started out as a physicist, took this brave leap into neuroscience.
Yeah, quite a leap.
And then into that crucial intersection of brains and AI. We'll dig into his insights, how they shape deep learning, and, what his work tells us about cognitive modeling.
And I think it's so important to see him as an architect, really. Not just someone who watched it happen, but someone who helped draw the blueprints.
Right.
Because, back then, the main idea of intelligence and AI was all about rigid, hard-coded rules, like a giant instruction manual.
Like programming every single possibility.
Exactly. But
Yeah.
Sejnowski saw it differently. He imagined intelligence as something more dynamic, something that emerges. From interconnected systems that learn, kind of like our brains work. And that intuition put him right at the crossroads of computational neuroscience and this burgeoning field of AI. He really brought them together.
So let's talk about that path. It wasn't exactly straightforward, was it? Starting in physics.
Not at all.
He got his bachelor's, master's, and PhD from Princeton. Impressive advisors, too, John Wheeler, John Hopfield.
Titans in the field.
But then he makes this pivot. Postdoc work in biology and neurobiology, first at Princeton again, then Harvard Medical School. That feels like a really bold move back then.
It was bold. Because he was stepping away from the mainstream physics track and embracing a totally different way of thinking about intelligence compared to what traditional computer science was doing at the time.
So that leads him to the connectionists in the 80s.
Exactly. He joined this, well, it was a pretty small camp back then, often kind of dismissed, the connectionists.
And how are they different from the dominant approach?
Well, the dominant thing was symbolic AI. That was all about programming logic, symbols, rules. Think chess programs solving math problems.
Okay, things with clear rules.
Right. It had some quick wins there. But symbolic AI just completely stumbled when it came to messy, real-world stuff, like understanding what you see or how language works or just basic common sense. You couldn't easily boil those down to rules.
So Sejnowski had a different idea.
He had this core intuition, which sounds simple, but was actually pretty radical. He basically said, look, the only proof we have that these hard problems can be solved is that nature already solved them.
Our brains.
Our brains. They see, they understand language, they learn constantly. So we figured the real path for AI wasn't trying to write down all the rules of thought, but studying the brain's actual structure, its biology, and crucially, how it learns.
And that led to The Computational Brain, his book with Patricia Churchland in '92.
Yeah, that book was a landmark. Because it didn't just theorize, it showed how the activity in these early, simple network models actually looked kind of like how real neurons respond.
Okay.
It demonstrated how you could distribute a task across lots of simple units, like neurons, each doing a tiny bit, but together producing intelligent behavior, a blueprint for emergent intelligence.
But people were skeptical. Right?
Oh, incredibly skeptical. They were basically told, this neural network stuff, it's a fool's errand.
A fool's errand? Why?
Well, the optimization experts warned them about all sorts of problems, like the networks would overfit, get too tuned to the training data, and fail on new stuff.
Right, they wouldn't generalize.
Exactly. Or they'd get stuck in local minima. Find a solution that seems okay but isn't actually the best one, like climbing a foothill instead of the mountain.
Okay, I see.
But Sejnowski and the other connectionists, they persisted because they had that deep belief grounded in how the brain works. And that persistence, well, turned out to be key.
So how did the fool's errand eventually turn into the deep learning revolution? Was it just persistence?
Persistence was part of it, but the big change was computing power. Suddenly, computers got vastly more powerful. They could do billions, then trillions of the basic math operations, multiplications, additions that you need to simulate these networks.
So they could finally build bigger, more complex networks.
Precisely. That exponential growth in computation let them explore what these brain-inspired models could really do when scaled up.
And what was the secret sauce Sejnowski identified?
It was learning through experience. That was the game changer. Unlike symbolic AI trying to pre-program everything. These neural networks, when you fed them tons and tons of data, they just scaled beautifully.
Scaled beautifully.
Yeah, meaning they got better and better with more data and more computation. It was less like handcrafting rules and more like letting the network discover the patterns in the data itself. That allowed them to learn functions, incredibly complex ones, that nobody thought possible before.
And that's when we started seeing real breakthroughs, around 2010.
Yeah, that was a critical threshold. Suddenly, this scaling paid off big time. You saw huge leaps in object recognition computers identifying things in pictures better than ever before.
Like tagging photos.
Exactly. And language translation took a massive jump. This directly connects to the AI we use every day now. And think how far it's come since then. Now we have generative AI making realistic images, having conversations. It's built on those foundations.
And Sejnowski wasn't just doing research, he was leading the field too, wasn't he?
Oh, absolutely. He's been president of the NIPS Foundation, that's Neural Information Processing System, since '94. They run the biggest AI conference every year.
Wow, since '94.
Yeah, and editor-in-chief of Neural Computation since '89. Plus, look at the awards. The Gruber Prize in Neuroscience, the Brain Prize. These are huge honors. It just underscores his influence across both neuroscience and AI.
So jumping to today's AI, like ChatGPT, Sejnowski has this really interesting take, doesn't he? That it mirrors your intelligence.
Yeah, it's a fascinating idea. Kind of flips the Turing test on its head.
How so?
Instead of us testing the AI, Sejnowski suggests the AI is almost testing us. The quality of the answers you get back often reflects the quality of the questions you ask it.
Ah, so if I ask a sophisticated question.
You're likely to get a more sophisticated, nuanced answer. Ask something simple or, frankly, kind of dumb.
You get a generic response.
Pretty much. It reflects your input back at you.
Yeah.
It's an interesting way to think about interacting with these models.
And underlying this is a deeper convergence, he points out.
Yes, this idea that AI and neuroscience are now starting to speak the same mathematical language, that's huge.
Why is that so important?
Because it allows for real crosstalk between the fields.
Yeah.
Genuine two-way communication. Advances in AI can now inform neuroscience, and discoveries in neuroscience can inspire new AI architectures. It's becoming a really symbiotic relationship.
So AI is actually helping us understand the brain now.
Absolutely. Deep learning techniques are becoming incredibly powerful tools for neuroscientists.
Like,
Analyzing those complex recordings from neurons, trying to reconstruct how brain circuits are wired together, mapping connections, connectomics. These areas have been totally transformed in the last decade, largely thanks to these AI-inspired methods. We're learning about the brain faster than ever before.
and it's not just academic, right? Sejnowski's work has practical applications.
Definitely. His research on brain-inspired computation has led to things like patents for blind signal separation, figuring out individual signals mixed together in noise.
Useful in many areas.
Very. And his work's been applied to medical diagnostics too, like using machine learning to help detect glaucoma earlier. That has real-world impact. Plus, think about understanding brain diseases like Alzheimer's or Parkinson's, and even improving how we learn that learning how to learn, course he helped create, has reached millions.
So looking ahead now, what does Sejnowski see as the future path for AI? He mentions transformers are great, but...
Yeah, he acknowledges transformers are fantastic, which they are, but they're mostly feed-forward information flows mainly in one direction.
like an assembly line.
Sort of. But he notes the newer models are starting to bring back recurrent networks.
Recurrent networks.
Yeah, networks where activity can loop back, creating feedback. This is much closer to how our cerebral cortex seems to work, with information circulating, which is probably crucial for complex thought and generating language.
Okay, so making AI more brain-like in its processing. But what's still missing?
He points out some really crucial gaps. One big one is the need for something like our hippocampus in AI.
The hippocampus for memory.
Exactly. But specifically for lifelong learning. The ability to keep learning new things over time without catastrophically forgetting the old stuff. Current AI struggles with that.
Okay, what else?
A huge one is the lack of direct sensory experience. AI learns from data, often text or images, but it doesn't live in the world, doesn't interact directly. This contributes to its lack of real common sense and understanding of cause and effect.
So it doesn't have that grounding.
Precisely. And related to that, he points out that large language models mostly mimic our cortex, the thinking part, but they miss the rest of the brain. The deeper subcortical areas like the amygdala, crucial for emotions, empathy, basic survival instincts, things honed over millions of years of evolution. AI doesn't have that evolutionary history or those drives.
Which is why it makes different kinds of mistakes than we do.
Exactly. It lacks that grounding, that common sense, those emotional filters. It fails in ways that seem bizarre to us sometimes.
But Sejnowski sees this as an opportunity.
Yes. He thinks identifying those specific differences, understanding why AI makes the mistakes it does compared to humans, is exactly how we'll make the next big leaps.
Interesting.
He emphasizes that AI evolution is happening at warp speed decades, not millennia driven by that exponential computer power. We're constantly exploring this new computational universe, as he puts it.
So to wrap up Terry Sejnowski's legacy, it's really about that bridge between brains and AI, isn't it?
Absolutely. He's a pioneer who consistently looked to the brain, nature's most complex system, for answers about intelligence. His work is a testament to how understanding ourselves can drive technological breakthroughs. A true founder.
And it feels like this conversation between neuroscience and AI, the one he helped start, is really just getting warmed up.
It really is. It's a powerful reminder that sometimes the most advanced ideas aren't brand new inventions, but insights gleaned from systems perfected over millions of years.
Right. So maybe a final thought for you, our listeners, to chew on. What happens when AI finally gets that lifelong learning Sejnowski talks about, or that embodiment, that grounding in the real world? What new abilities might emerge then? And how might that change our own definition of what it even means to learn, to adapt, to be intelligent? Something to think about.
Thanks for listening. If you enjoyed this episode, please like, subscribe, and share. It really helps us grow. See you next time.